Oh,
Yeah, I'll kick it off by just introducing myself. It's Paul Lucier. I work for Palitronica. We're out of Waterloo, Ontario, Canada, and very pleased to be able to spend some time with you today. I joined Dr. Sebastian Fischmeister about 2 months ago at Palitronica, and Palitronica was spun out of the University of Waterloo's electrical engineering lab, which Sebastian ran and continues to run today. It's very novel technology. Hopefully, it'll be a new technology for you. We think it is definitely something that has potential to have great benefit in the supply chain security as well as operational assurance and seeking out things like malware and ransomware. So I will turn it over to Sebastian to introduce himself as well.
Excellent. Yes. So I'm Sebastian Fischmeister. I'm a professor at the University of Waterloo, and I'm the CEO of Palitronica that we spun off from the research work that Carlos Moreno, co-founder of mine, and myself created at the University of Waterloo. And I'm excited to give you an overview of the technology, what we know so far about the systems and their applicability. And I'm happy to take questions throughout the conversation. All right, so let's jump right into it. And I assume that everybody sees the slides. Palitronica detects cyber attacks on critical physical infrastructure and also the supply chain for the critical physical infrastructure. That means the technology that we created aims to protect fighter jets, armored vehicles in the same way that it protects for example, water filtration systems and also transformer stations in the power grid. And you will see how we do this, that we can span this whole spectrum of these different types of systems. And somebody has a mic on there, and let me know if all right. So fundamentally, it is clear that cybersecurity is a challenge, and especially in the industrial control systems and the operational technology and the platform technology sector, we have very much these challenges. It has been named a clear threat to national security if you fail on your cybersecurity side. You have seen that past cases with incidences where fines were issued and payment was made up to 300 million in damages for a single incident. And the challenge why it is still a problem is because the critical infrastructure that we have in place nowadays is bespoke. It has individual solutions, and you cannot just add cybersecurity on it after the fact. Think about it. Would you add, for example, Norton antivirus or any type of antivirus to a pacemaker that you intend to implant in your body? Most likely not. And the reason is because these systems undergo heavy certification and qualification efforts and have to function in the specific scenarios. In addition to that, cybersecurity is this never-ending battle where you have spiraling costs because constantly new devices are brought onto the market, added to systems. And unfortunately, everybody right now assumes that more of the same, meaning more of, for example, network intrusion detection, more event capture and so on will help. But unfortunately, all the low-hanging fruit in this area is already really taken. It's a very saturated area. And in our opinion, you need something different from this. We need to attack the problem from a different angle. And that is something that we have done, where we look at a fundamentally different approach and look at the physics level of systems to provide cybersecurity. There are two particular problems that we address with the products that we have. One of them aims at the supply chain, looking at whether we trust the hardware. And the other one looks at the runtime behavior, where we look at whether we trust whether we can trust the system at operating time. The problem with trusting the hardware is as follows. The question is, does your hardware have integrity when you buy it? Did you actually get what you ordered? And the reason why this is a problem is because today we recycle e-waste, meaning that we sell our electronic waste to another continent. On that continent, they desolder the hardware and then sell it to somebody else. That person sells it back into the supply chain by mixing it with good parts, and suddenly your e-waste enters into the supply chain as new parts. Another problem are counterfeit, where there's 5 new types of counterfeit recognized each week by a single organization in the US. And we did our studies ourselves, and you will see quite some shocking numbers afterwards on the number of counterfeit in a single purchase. And of course, the third problem are hardware implants, where you have to investigate whether somebody has intentionally modified a microchip that they sell you such that they can later on, for example, disable the system or make the system perform in a particular way that discontinues the service and thereby disrupts a critical service or a critical piece of infrastructure. What we have to address this particular problem, and I will jump to this particular case here, is what we have developed to address this particular problem is a supply chain protection technology based on physics. That means you can see a modern electronic system like a large cave. If you shout into a cave, you can listen to the echo. What we do is, and if somebody modifies something in the cave, then the echo will change, which you see in the lower portion of the figure. What we do is that we listen to the echo and compare the response on the echo to a known good behavior, which can be either created through a previous sample of that piece of electronic that you have, or through, for example, destructive testing of the system so that you have one gold master and understand that that's what you want to buy. Now, this looks like a very simple analogy, but actually it works very well. So what we have is a technology and a test station where you receive a part, you place it on the test station, we ping the device, listen to the echo, and then tell you whether you can use this part or whether you have to execute an incident response plan. The way that this technology works is non-disruptive, black box, vendor agnostic. The reason why it works this well is because our low energy pulse that we put into the device does not change the fundamental of the electronics. It does not activate any of the circuitry. It stays below the 0.5 volt range. And thereby you can apply this to qualified components and assess them to see whether they have been modified. Examples of what we can detect is attacks on the supply chain, like somebody modifies electronics, inserts either, for example, a modification on the hardware side and then combined with the second technology we have also on the firmware side. We can identify counterfeit parts. We can identify backdoors as well, both on the firmware side through tampering and on the hardware side. Let me jump to the result to show you what we know there. We analyzed 220 microcontrollers that we bought on the open market from 7 different vendors. 54% of these were counterfeit. That means 54%, 120 chips were counterfeit. Our technology of the pin to ping the chip was able to identify every single one of them. Even better, we were able to identify which type of counterfeit it is, because there are more types of counterfeit out there than is available in the public literature. To add even more to that, we were able to identify lot codes and tell you whether the printing on the chip corresponds to the lot code, or whether somebody is selling you, for example, extensively long stored chips that they now throw on the market.
Hold on a second.
Yes. Oh, a question.
Carol, did you have a question? Okay, sorry, go ahead, Sebastian.
Right, then, okay, yeah. So because of the current chip crisis and a shortage, you will see that everybody looks into their warehouses, what kind of batch of chips they still have available, and throw them onto the market. We had requests from like a company in the aerospace side where they say we have to buy this $100,000 a pop chip. Our main supplier doesn't have them anymore. When we look online, we find like a supplier from Azerbaijan, but we have no clue whether that chip that they sell us is actually what we want and is actually what we can use for our system. Just to show you a concrete example there. Are there any questions on the supply chain side before I now move into the runtime part? If not, then I will jump to this particular second piece. So what we do for the runtime protection is that we use, again, physics in order to identify whether systems are operating normal or under cyber attack. The way that we do it is by observing the power consumption of these systems. Systems consume power in patterns. We monitor the power patterns, and an attack on the system will disrupt the pattern of on the system. And so here you can see an example of an attack where it disrupts the system. It's obvious to you from this point of view, and if you can clearly see it, well, our algorithms can also identify it. There are a couple of patents pending and awarded on this topic. So what we built is a technology then that can monitor your system and at runtime and tell you based on the power consumption whether the system is operating normal or is experiencing a cyber attack. It is able to protect agentless devices. We have shown that we can protect PLCs and other types of systems, and you will see extensive examples later on. The technology is retrofittable and it is non-disruptive. It is also safe because we don't have to install any software on the system that we protect on the endpoint, and we are actually galvanically isolated from the system that we protect. We have shown in the past on existing systems that we can detect hardware tampering. We can also confirm the readiness of a system, and we can also at runtime assure that the system is operating normal, and you will see a couple of examples on there what that means for this. Any questions on this basic technology to monitor the power consumption and identify cyber attacks? If not, then I will jump to what we know and what results we have seen so far. We know that the technology is applicable to IT systems. So here you can see power traces during a startup, and you can see a ransomware attack in the system. In a ransomware setting, our detectors are placed like earthquake sensors in an organization, and we see the similar patterns then on multiple machines. And based on that, identify the ransomware and can tell you that you experience a ransomware attack. We have overall shown that we can detect social engineering attacks where somebody plugs in, for example, USB sticks like the USB robot ducky. We can detect the evil maid attack, somebody bypassing the operating system, changes to the BIOS security settings, rootkits, whether that's Rakshasa or LoJax, ransomware, and in general anomaly detection on the power consumption during the boot up. We can also and have also applied it to operational technology and industrial control systems. So there you see an example of an Allen Bradley system and a Siemens Simatic system where we can identify reprogramming attacks on the firmware of the system. It's you can clearly see the drop in the power consumption as somebody is reprogramming the system. And if you can visually see it, our algorithms and systems can pick this up, and you can see it here in a bigger context as well. We can identify out of schedule power cycling and system reboots, and all of this without changing the certification of the system that we monitor, without installing any additional piece of software, without changing anything in your approved network topology. We have demonstrated that we can apply it also to appliances and IoT systems. So here you see a Netgear wireless router, and we can identify the individual stages that a Netgear router is in. And thereby we can again identify firmware uploads, deauthentication attacks, denial of service attacks in general. We have also shown that we can apply this to communication equipment, and we have shown this on Cisco routers and HP switches. And you can see in the in the first upper figure here that we have the red line shows the original firmware, and then the blue line shows modified firmware, and you can see the difference in the power consumption. And that's something that we detect besides other things, like, for example, attacks on logs, meaning log falsification and injection. We also detect if somebody is, for example, using the system to spy on the network. And finally, we have shown that this also applies on platform technology. We have tested it on a Canadian land platform and on an aerial platform as well with MIL standard 1553. You can see different types of attacks here, whether that's now a service disruption attack, whether that's a termination, so denial of service attack, or whether that's stuttering to break the quality of service of, for example, a target tracking application. We have demonstrated that we can identify firmware updates, BIOS changes in the system, denial of service, alteration of service, and replay attacks as well on this particular on systems. Any questions on the technology so far? If not, then to show you the vision, what we are currently doing and where we are going, the goal is to develop an universally embeddable physics-based security module that can be integrated into existing infrastructure, or that can be added into new infrastructure purchases in the future, or the existing external modules that we have can be added to already existing infrastructure. You can see that we have already a good setup of systems where we have demonstrated the capability with additional partners and systems lined up for this year and the near future. And with this particular slide, I would like to end the presentation and open it up for a discussion for any questions that you have.
I was wondering, this is Yolanda Dari Carrera. You mentioned the detection. You're focused on the detection. So I'm wondering, is there any inception to, with the detection, does this only provide an alert, or does it halt the activity of the technology? Does it stop? Does it interject? Or put a stop to, I guess it's already, it's already installed. So I'm just wondering, is it merely a detection tool? And then you would have to go back and with your team to determine on remediation? Or does it offer something else?
Yeah. What it offers is also, we can also add the response to it by, for example, allowing you to power cycle the equipment. Or, for example, by working in collaboration with a network switch, that you can isolate that particular device.
Okay, yeah.
However, what we have found so far with the customers that we worked with is that cutting the power and power cycling the equipment on critical infrastructure is not necessarily something that you want to automatically have done, because in many cases in critical infrastructure, you want to be alerted that somebody then looks at the response, which has to be specific to that type of alert, and not just suddenly shut down the whole system.
Right. Well, what about a rollover? Does it offer like, is the, I guess it depends on internal policies, but they can roll it over to a hot spot or a cold spot or something like that.
Yes, let me show you. I'm not sure whether I have it in this particular slide deck here. I will share in a moment again. Let me just open the other slide that you can see what that looks like. All right. Please let me know if you see the current slide here.
Yes.
So the way that it works is that we monitor the power consumption, in this case here, of the Siemens system and also the Bradley and also the Ethernet switch. Our detector boxes stream the data into a secured cloud infrastructure. And when we find and identify alerts, we notify a third-party SIEM or SOAR solution. It's not that we try to replace existing SIEM or SOAR solutions that you might already have. We can stream our alerts into an existing infrastructure and thereby allow you to leverage the investments that you already made on that side and now get additional information on the individual piece of infrastructure that you want to protect. So whatever response you have in your SOAR, we can feed information into that SOAR. And I saw there was a question in there. Should I repeat the question, or how should we proceed with this? So let me.
Or I can read it. Are you referring to the Bill Garner question?
Yeah,
Yes, correct.
I can say it out loud too.
Oh, there
You
you
can hear me.
Sure.
go for it, Bill.
Yeah.
So interesting. What I'm getting is that your baselining behavior, this is based on power consumption of the end device, and that you're sniffing that right off the wire, right? But that means you have to be in line with the end devices to see that.
Correct.
So
yes.
if you're on a segment and there's multiple devices on that segment, how do you differentiate between them? That's one curiosity I have. And
yes.
So, I mean, in other words, you're at a choke point where you're monitoring the actual communication. This is Ethernet, right?
What do you mean? So what we do is we monitor. So what you see here is the cable. One of them goes back here to the PLC, and the other one goes up here to the power supply. And then the same thing on the second one. This one goes up here to the switch, and then the other one goes to the power supply. So we sit in line with the power supply for the device that you would like to protect.
Okay, so it's not an Ethernet or packet base. It is actual power of the individual devices. Does that mean we need a sensor for every device?
Yes, and that's why
okay.
In the long run, we are looking to miniaturize this to work with companies on the power supply side, that we can directly integrate this already into their power supplies, into their power supplies.
Right. So it's like source labeling, but different application. Okay.
Yeah.
Thank you.
At the moment, we offer it as an external box that you can use and retrofit to, for example, protect PLCs that that control ozone filtration pumps and so on in the water supply and other types of similar types of systems. All right, there was a question from Simon Hartley. The baseline for a particular environment, what constitutes normality? Are there false positives? Devices get fractional hot in a vehicle in summer. So we create the baseline during the system while we observe the behavior of that system. Okay, I see more questions coming in, but let's address one of them at a time. One important aspect is that a number of attacks that we address and identify are during the boot behavior of the system, where we can immediately identify firmware modifications and, for example, changes to the security configuration of a system. This does not drastically change between the individual devices and between the individual runs. So that has a very clear pattern and a very clear behavior. For behavior in IT systems in a general organization, that is something where we deploy multiple systems, like, as I said, like an earthquake, like earthquake sensors, such that we can filter false positives in case some person watches, for example, now or downloads a YouTube video and does video transcoding on their system, which might look similar on the signature, like Infinity Locker or something else that, for example, encrypting your hard drive. And that's how we filter out false positives on general compute systems. What constitutes normality? So for during the boot up phase, we just have to get a couple of boots of a system in order to build a very robust and precise model of what that system looks like. You would be surprised how deterministic a boot is of a system, even of a general computing system. Once you go onto the OS side, that's when it becomes more difficult. And that's why we then deploy multiple sensors and do correlation between these particular systems. What class of attacks do we support? We support attacks both on the hardware side. So that means insiders, in that sense that they got tricked into, for example, plugging a device into the computer. Let's say you have, for example, a USB stick plugged into the computer. Next time the system boots, the USB stick, for example, then modifies either the BIOS or adds something to the system. And that's something that we can immediately identify. We also identify hardware-based attacks. We have demonstrated this if somebody, an employee, for example, goes in and changes systems, which is a challenge when, for example, you are in a water supply site, you have external contractors coming in, you can't monitor them all the time. They are next to a particular piece of equipment, and you want to make sure that, well, afterwards, your system is still in the same state as it was before, except for that particular fix that they did, and not behaves in a different way. Other types of attacks that we can identify are, as I said, firmware reflashing, denial of service attacks on the system endpoints. We have not crosswalked all of it through MITRE ATT&CK. I'm familiar with also the CAPEC database, and we have looked at that already. It's something where we have a document that was created a while back where we looked at the different types of attacks, which ones we can cover, but that is something that would need to be updated.
Hey, how you doing? This is Kevin Green. I asked the questions. The other thing, the second part of my first question is, are you expressing any of your detection findings in the form of CWEs or anything?
So what we do is when we find, so we don't have reasoning on top of this, that we cannot at this point yet suggest you what then the IOC is for a particular novel attack, or what the or what the response should be immediately to this. We currently are at the phase where we identify the abnormal behavior of the system, like for example, the deviation from the boot behavior. And we identify also at runtime, for example, the ransomware side, and we then leave it to the source system in the backend to have particular reasoning and responses to this. We are also not at this point create threat intelligence where we say, oh, this is the indicator of compromise for Infinity Locker. That's what it looks like on the power side. That's something that we currently still not share and do not give out.
All right, I think you misunderstood my question, but I'm glad that you shared that, because I do think the threat intelligence piece. But in terms of common enumeration, common weakness enumeration, is basically, MITRE has extended their ontology to support not only just software but hardware. So I figure, if there's a way to kind of have the mapping, because obviously it helps with mitigation. So a CWE helps identify like what the issue is, and it kind of helps with mapping to CVEs and KPAC and everything else. One of the things I would suggest is you contact MITRE, and maybe part of what join the community, and probably try to be part of the CWE board, because I do think if you're producing detection, if you're producing findings, trying to categorize and express those findings in a way where we're building that knowledge and that common knowledge and bringing awareness around the community, I think that would be very helpful.
Yeah, and thanks for bringing that to my attention. I thought first you said CVE, like the common vulnerability
No, CWE
database. And so that's why I didn't fully understand whether we report then to CVE, like create entries on the CVE side and say this is what it looks like. No, and I will definitely look at the common weakness enumeration and follow up on that.
If you're interested, I can make an introduction. I used to work at MITRE before coming to Parasoft, and I supported the CWE program. So I can make some introductions if you want, and that way you can kind of get acclimated. And I do think they are trying to, expand the hardware side. So I think this may be, a good opportunity to kind of, provide better awareness around what you're doing and also help educate the community.
No, it would be fantastic if you could make an introduction. Yes. There was some other question. Oh yeah, a point on Terminator. All right, it's great. Thank you very much for the reference. I'm not claiming that we are the first one who have done this. To give you an idea, in 1982, a prof from Stony Brook already identified that you can use power tracing on to identify changes inside FPGAs and basically programmable hardware, which is actually really novel for given that that was like in the early 80s. Out of this came this whole work on power line disaggregation and figuring out, oh, did somebody turn on the toaster or did somebody do this or that in the house? So the idea has been around already for some time. We are now bringing this onto the market and demonstrate, because we demonstrated that we can identify interesting information, cybersecurity relevant information, and attacks on systems.
I have another question. Have you looked at any use cases for automotive?
Yes, I actually have a lot of background in automotive.
The reason why I say that is because the new ISO standard, the 21434.
Yeah.
A large part of the standard is focused on design, is focused on, doing a TARA, threat assessment, and all that other stuff. So threat modeling. So I do think you have potential data that can help support and kind of, provide, information and inform about design and stuff like that.
No, it's a very interesting thing, and we can look up there. I'm happy to follow up on this. One of the challenges in the automotive sector is if you want to add something onto the vehicle at runtime and it costs more than 25 cents, then they already roll their eyes, because the automotive sector is extremely price sensitive on this. And But on the supply chain and on the non-recurring engineering side, then that's a good point to follow up there. Yes. Thank you. One point also, David Curtis asked the question, what is the utility of the solution to unclassified IT systems, support for end users and laptops, network management teams, data center, and so on, and cloud infrastructure teams? So similar, we actually have tested this on network switches and on IT laptop systems. The challenge is that these systems, the classical cybersecurity packages that you have on these systems only gets activated once the system is fully up and running, meaning once Windows has loaded the appropriated programs for this and starts the protection, which is early in the boot cycle, but still not at the time of, for example, the BIOS or UEFI load process. And so what we can add to this is that we can allow you for critical pieces in your infrastructure to add these sensors like tripwires, where the attacker has no way of knowing whether you are currently monitoring this system in this particular way through the power supply, because they don't see it on the network side, they don't see it once they are on the system. And so therefore, we allow you to install these like tripwires to catch APTs that might sit in your system and might spy on your system and, for example, prepare for lateral movement. One clarification also on this is we are not trying and not aiming to replace your classical endpoint protection, even though it consumes 80% of your or 50% of your CPU. Any other questions or comments on this?
This is Paul here. I just wanted to jump in and say, obviously this is not a product pitch type of scenario, and we wouldn't be able to pitch to you anyway because we don't have pricing, we don't have a full solution, and we are looking for opportunities to prove this technology out. So we are very much in the proof of concept phase. We are working with the Canadian government on a couple of projects right now. One is with avionics and one is with land vehicles. We're also looking at doing some other work. We've got about 4 government projects through the Canadian government armed forces, but very much looking to expand that and for ideas. If we're very interested in knowing if there's any areas you see this applicability making sense. We want to make sure that we create a solutions that are going to solve problems today. So we think it's exciting technology, but it's not fully formed yet into a solution. And therefore, we welcome any opportunities or any follow-up discussions where you see there might be a good fit.
So this is Dave Curtis. Can you hear me?
Yes.
Yes.
Yeah. So as we're wrapping up, I just want to say that the reason I asked my question the way I did is because when you start looking at an unclassified, operational environment for what essentially is the government attack surface, which is primarily the unclassified environment, you've got contractors who provide a lot of your hardware, and you've got cloud providers that provide a lot of your infrastructure, and to need access to get between the processor and to get on the same wire as the power supply, or to have a sensor at hardware level for those devices, it may void a contract or warranty, or you may not have access to the hardware at all. So that's what I was saying. I think it would be useful, if you had a deck that talked about the environment that I described there, where I've got people, we've got people that deliver laptops to the staff, right? So they could do something to scan that laptop. I'm sure you could facilitate them, running some sort of a scan on that laptop, to come up with a footprint for it that then you could run against it later or something. There's some things you could do to support those managers who do the end user support on laptops, the guys that do the network management team. He's got Cisco routers. Now, what you know, I think you need to develop your use cases for those particular personas of the unclassified IT network, IT system managers for those different categories. That's what I was alluding to in the question.
Let me address some of that, or try to answer that. One thing that we have also now available is a software version of the power tracing part. And what you can do is you can easily roll this out in your infrastructure, and then we collect power traces from them. And yes, we can analyze power traces directly, but you have the similar problem as with any other software-based solution, that when the attacker takes over the host, then they can immediately disable endpoints or try to basically fake data to the endpoint. But the great thing that we can do is, what we do is we can use the software collected power traces and compare them, for example, at checkpoints to the power consumption that the system has at this particular checkpoint. So we can in software create these profiles, and then at a particular checkpoint, like for example, in the IT shop, when they get systems back, or at a particular entrance and so on, you could plug this system in and compare the power consumption to the particular profile that you collected. So that's one interesting novel approach also that we have there to address the point of adding a box per device. That's one aspect. The other one is, as you move towards DC in data centers, so direct current, it will become very easy for us to be in line with the servers and with the network equipment that you have in there. We have seen already large companies like Facebook and others switching to or going into the direction of DC power supplies in the DC distributed power in the network, in the data center, and that's one additional use. However, primarily for now, we thought of applying this on the OT side for critical physical infrastructure, not your typical cloud setup. One other question, and I see somebody read our press release on the website on the Avionics Project. So what that project is about, it is about identifying, securing the supply chain, and also testing the viability of this technology to protect fighter aircraft in the Canadian Armed Forces. That's all I can say really at this point. When you looked at it so far, what we have, and at the technology, I think you can already see how this is applicable there to assess parts and identify tampering. And if you look at the runtime piece, then you can also, I assume, guess a little bit what we can do there. Other questions from the audience?
I see Marvin Wood asked if you could give more detail on the Canadian Avionics Project.
Oh, that was what I just said.
Oh, sorry.
Yeah.
Never mind. Any other questions? Thank you guys. This has been really great, and I appreciate the discussion from the audience as well. Okay, well, we're almost out of time anyways, and this presentation will be available if you want to review it, or if you want to send it to someone who you think it'd be helpful to. But otherwise, I want to thank you, Sebastian and Paul, for meeting with us, and everyone for joining. It's been a pleasure.
Thank you very much. And thank you very much for everybody else for the questions and also for the feedback. And yeah, I'm looking forward for the connections that come out of this. And if you have any additional questions, feel free to reach out to Paul or to me.
Yes, thank you, Kirsten.
Thanks, everybody.
If you could provide me with a copy of the recording, I would be very grateful. And please feel free to give my information out to anyone who's interested.
Absolutely, will do. If you guys want to send me your slide deck, I can send that out, and then people can reach you that way.
I'll send you a PDF of that later today.
Perfect.
Quick question.
Thanks for your time, everyone.
What is UW Labs?
Oh, sorry, that's the University of Waterloo. So that's where
okay.
I'm a prof at the University of Waterloo at the moment. That, by the way, shows you that we're not dependent on Amazon or any kind of large infrastructure at the moment. We can still all of this host ourselves, which also allows us to host this on the edge or even on like more mobile systems.
Yeah, just to add, University of Waterloo, if you're not familiar, is about an hour west of Toronto. It's commonly referred to as the MIT of the North. And it's one of large engineering and math faculty. Well, I think it's the largest math faculty in the world.
Yes. We have the second largest engineering department. And I think if you know another stat there, we are the #2 supplier of new hires in the Silicon Valley area because of the excellence that we have on the engineering side. So when you go to San Francisco and you go around between on the different companies, they all know University of Waterloo because of the many hires that they have made out of our graduates.
And now he's just bragging.
Yes, of course I had to add this. No, it's just I find it fascinating that we have that, but that's not Palitronica anyways. All right.
Thank you for your time, everyone. It was great to be able to present to you.
Yeah.
Thank you very much as well, everybody, and have a nice day.
Thank
You
you.
too.
Bye-bye.
Thank you. Bye.
Bye.